And this is our first talk in a little bit after a bit of a break. So I'm pleased to introduce Pete Siemsen from Front Range GigaPoP and NCAR. And today he is going to be talking about implementation of BCP 38 with uRPF on Junipers. So it's all yours, Pete. Take it away.
Okay, good afternoon. I'll just jump right in. We'll talk about what we're trying to do. The basic problem is, how do you prevent spoof packets coming from your customers going out to the internet? Or how do we approach the problem of spoof packets with an eye towards things like mitigating DDoS attacks and so on? So for the purpose of this talk, I'll assume that you guys are an ISP or a regional network, which amounts to the same thing. In other words, you guys are the good guys. You're running the internet. You've got customers connected to your network, and you're providing access for them and service for those customers to access the internet. And let's suppose for a moment that you have some of your customers might be they might be students at universities, or they might be other kinds of interesting folks that have some bad guys, some guys that might source DDoS attacks or have some other reason to source packets and try to fool the internet about where those packets came from. And they create packets with fake source addresses, and they emit them to you as the ISP. Or maybe it's not bad guys that are out to do it on purpose. Maybe it's just PCs that have been infected, and those PCs are running software that sources bad packets. Or what we've discovered too is that it could just be that there's some misconfiguration going on, and that your customers are leaking bogus packets towards you. So you forward them to the internet suffers in one way or another. And with the fake source addresses, of course, it makes it hard for people out on the internet to go back and track down the bad guys through you and try to make the problem go away. So the basic point of the talk in uRPF and BCP 38 is that we should try to defend the internet from the bad guys, and we're looking at uRPF as a mechanism for doing so. So this talk is titled, What is BCP 38? Now, best common practice is number 38. We probably all know all about this, but I'll mention it just for a moment. The internet is based on these defining documents that include RFCs and BCPs, best current practices. And they're just kind of the summation of the best information we have on how to deal with certain problems and what ISPs should do to keep the whole internet running. So BCP 38 is document number 38, and you can click on that link if you've got the live slides on, or you can just Google for BCP 38, and the first hit will take you right to the document if you're interested in the details. The title is Network Ingress Filtering, Defeating Denial of Service Attacks which employ IP source address spoofing. So the idea is that you as an ISP want to help keep the internet running and block denial of service attacks by only forwarding good packets from your customers. In other words, if they have bad players in the sites, you don't want to allow them to send you packets that have spoofed source addresses. Good packets that you see from your customers are ones that match, where the source address matches the IP range that your customer has, so nobody's trying to pull a fast one, and you should just block all the other packets. Now, if everybody did this, it doesn't mean denial of service attacks would go away, but it's a pretty good step in the right direction, because it would make denial of service attacks easier to prosecute or easier to track down and defend against, assuming that there's people that are trying to do that. So one way to do this is kind of tedious. It's what BCP 38 mentions without talking about uRPF. It just says basically that as an ISP, you should put packet filters on your interfaces that go to your customers. And what those packet filters look like is, okay, since you know the source address blocks that your customers are advertising to you, you know what sources are valid from your various customers, you just put a filter on every one of your interfaces, and you only allow packets from the customer that have source addresses that match the blocks that they have. That's fine, but the trouble is, if you actually do this, you get into a little bit of a management problem, because you end up having a packet filter which lists the IP addresses that the customers are allowed to send you, and it looks a lot like the BGP filter that you have on your BGP connection to the customer, where you're filtering what routes they are allowed to advertise to you. And of course, whenever you have a case of two lists of blocks or IP addresses or whatever, you may end up having problems keeping those in sync. And when they fall out of sync, things get crazy. It just feels kind of bad once you've implemented this, to every time a customer asks you to make a change and to adopt either add or drop an IP block, then you've got to go and update two places in your router. You can probably make this work. I'm sure many people do, but it's asking for trouble in the long run. So there's a solution. It's called uRPF, unicast reverse path forwarding, and it's just a kind of a trick the router vendors have put together, where the router, instead of using a straight packet filter that you have to maintain, you just tell the router that you want it to start filtering using the information the router already has about the packets that are coming in on your custom interfaces. So since you're already learning routes from the customer, uRPF just uses those routes as the list of valid source addresses that should be in the packets that are sent to you from the customers. By implementing this, it takes away the problem of having redundant tables in your routers, and it also makes it so that it's easier whenever the customer starts advertising a new route. You only have one list to change. So it's kind of sweet. So what the router does is, when the packet arrives at the interface from your customer, the router looks at the packet and says, okay, I can see the source address and I know the interface the packet came in on. If I would feasibly use that interface to send an answer back to the customer, then it's a good packet. Then it makes sense. It doesn't sound like anybody's trying to pull a fast one. And so we're going to accept that as a good packet and do what we normally do with it. If it's not, then we'll do something else about that packet. And I'll talk about that in later slides. So in Juniper's implementation of uRPF, you turn it on, and I'll discuss how to do that a little bit later. And what the router provides to you as a system administrator is an option of what to do about these bad packets that it recognizes. So the router can either log the packets and forward them as it normally does, or it can block the packets, or it can both log and block the packets. And having this capacity to log the packets instead of just a simple-minded blocking is a very good feature for us as ISP administrators, because it allows us to take a look at how bad the problem is without affecting anything, and then move on to trying to fix it. So that's something we took advantage of at the FRGP, and I'd recommend that you do if you consider implementing this. So you can try before you buy. You can log the bad packets, look at them, maybe try to fix the problem with other mechanisms, like informing your customers about the problem and letting them filter the packets, which is a good thing. Doesn't mean you shouldn't also block and filter the packets, but it does make for a nice clean option to block the packets closer to the source. And you can log and you can block only. It's also flexible in that it lets you implement it per interface. In other words, you don't have to do this and turn it on and all of a sudden all your customers instantaneously feel the effect if they would normally feel the effects. You can do it on a per interface basis. So you can choose to do one customer, even if they have more than one interface. You can do sets of interfaces at once. And that's what we did at the FRGP, but we did it not for technical reasons, but more for the management kind of reasons that I'll go into a little bit later. And it's implemented like other packet filters in the Juniper. So it's kind of like a really smart rule that you can stick in, but you can have terms in the filter so that you can choose to do things with packets before they hit the discard statement or the syslog statement. So you can selectively choose to let certain packets through the filter without being checked if you need to. And that's useful to take care of some little issues, and it's also something you might do when you're debugging and playing around with this whole capability. There's some challenges. One of the things that seems to crop up immediately is that most network engineers, when they hear how reverse path forwarding works, they say, well, this will never work for me. I've got some asymmetric routing. I've got a customer that has two interfaces that connect to me. And although the packet might come in one interface, my router's routing tables would tend to make the return packets go out a different interface. And so this can't work for me. I'm just going to go on with and do things different ways. So the solution is to use the feasible path option. There's two kinds of unicast reverse path forwarding. There's the strict kind, which is what we've talked about so far. And then there's the feasible path kind, which says if it's feasible that you might send a packet back to the customer on that interface that I'm looking at, then it's a good packet. And of course, that's what we use, and I think that's what most people use to solve the multiple path problem. Also, I should just mention now that we don't do reverse path forwarding on our provider connections. There's too many routes to consider. We just use this to deal with the customers that we have behind us. So if you're going to go off and start implementing this, what does it look like? Well, here's what you do on your interfaces in order to turn on reverse path forwarding. That line that's highlighted there, the RPF check, fail filter, RPF fail discard. What that means is apply RPF checking, and the filter that you should use to do the checking is named RPF-fail-discard. So this is the thing that you do on each of your interfaces to turn on RPF, and that RPF fail discard filter looks something like this. Ours is a little bit longer than this, but I've whittled it down to make things fit on the slide and be nice for this presentation. So in this case, our RPF filter says we've got a whitelist, a term that covers a list of prefixes that we, for some reason or other, explicitly want to pass and accept without doing the RPF checking, and then any other kind of packet will fall through into the RPF section at the bottom, the term final actions. And what we'll do with those packets is count them, syslog them, and discard them. So in this case, we've already been through the procedure that I'm going to describe a little later for how to start from nothing towards doing full uRPF. We've been through it now, so we're discarding packets, and we're logging them still just kind of for informational purposes, but we're throwing them away. And obviously all you have to do is remove the syslog line from this filter to stop logging. And if you remove the discard line and put in accept, then you can accept the packets. So you can choose to log them and accept them, which is very useful. Third thing you have to stick in is this little set of lines has to appear in the routing options section of your config, and that tells the router to use the feasible paths option instead of the active paths option. So the active paths is when you're doing strict checking, where you're just doing the kind of simple-minded checking, and feasible path says do the more involved look at inactive routes as well as active routes. So if you do this in your routers and you have logging turned on, this is the kind of log messages you'd expect to find in your syslog file. You let the router run, and as you can see, these log messages have a timestamp. I'm not sure, I guess, oops. There's a timestamp at the front. There's the IP address of the router that is emitting this log message. There's some other gobbledygook, and then there's the interface that we're talking about. The D means that packet was discarded. This is the protocol that's in use. The destination address, the source address, and the destination port and source port. And the router will actually roll these up a little bit, so it won't give you a single log message for each packet. It'll actually count them up. And so in this case, there were 3 packets that match the signature, and we got this one log line for that at that timestamp. And then there's another one that's pretty much the same thing. It's just the protocol's a little different, the ports are a little different, the IP addresses are a little different. There was only one packet. So these things will start appearing in your syslog file, and it's up to you to decide what to do with them if you're interested in the logging feature. So when you consider doing this, you have to step back and ask how you're going to do this in terms of your customers. So at the FRGP, we have about 30 customers that are connected to the FRGP. Our network was running fine, everything was great, and we decided that we wanted the FRGP to be a good citizen. So like other ISPs or regionals, we have some way of communicating with our customers. We have a website, we have meetings every, say, 6 weeks or so. And so we broached the subject to them and said, do we want to start actively blocking packets. The FRGP historically has always taken the stance that we just forward packets for our users. We don't do much with those packets because we don't want to disturb the users. And some of our users do some things that are interesting with research projects having to do with BGP and so on. So we're very sensitive to their desires about what we do with their packets. So we said, well, the FRGP wants to step onto the good side of the line and join the group of ISPs that are protecting the internet and cut down a little bit on the DDoS attacks and so on that might come from our customers. So we got them all to buy into the general idea that we want to be a good internet citizen. And secondly, there's really not a good reason for you to be emitting packets with strange source addresses. And we laid that out there and, of course, had a nice discussion about it, and nobody could really come up with a legitimate reason to do that. And so with that kind of agreement, there should be no reason that they would have complained about us blocking their packets. So we also said we're going to introduce this to you slowly. We're not going to dump it on you. We're not going to force it down your throat. We're going to let you start dealing with this. If there's no legitimate reason for you to emit bad packets, then wouldn't it be nice if we tell you about what bad packets you are emitting and let you go off and take a look at fixing that? Because technically you shouldn't be emitting any of those anyway. You can take care of your dirty laundry without any issues going on. And then there'll come a flag day, and we defined that day. It was a year or so ago, when we said, okay, now we're going to change, and instead of just logging and forwarding the packets, and we're going to start blocking them. And that gives you lots of warning time and plenty of announcements about what we're going to do when. So, okay, that's great. We have log messages in our syslog files, but that's not any good to the customers unless they can get at those. And the customers, of course, don't really want to start parsing all those log files individually. So we wrote a Perl program to help them do the job, to kind of roll up the syslog files and give them some nice statistical descriptions of what's going on with their site. If they're not emitting any bad packets, then they wouldn't see anything in our reports. And if they were, then they could take a look at how to fix them. So the easiest way to do that, we have a website. I'm sure every ISP has a website. And we wrote a program that parses the syslog files, writes HTML files to summarize everything, and puts that on our website. And that gives them a great way to look at the problem individually for their own site, and maybe solve the problem and sidestep the whole issue of when we were going to turn on our blocking. So the program runs once a day. It just simply replaces a set of web pages. There's a web page for every customer, and so you have a 24-hour block of time to look at it. So when the customers would go and experiment with fixing the problems, they did have to wait a day to find out what the effects of their changes were. But that's just kind of the way that system worked for us. Technically, it's hooked to the log rotate system on a Unix box. As you probably know, when the logs are rotated and time-stamped and set aside by the system every day, there's an option to run a script after the log file has been rotated. So in other words, right after a log file that represents 24 hours has been put in a directory and a new log is started, right after that happens, the program runs on the old log file from the last 24 hours, and all the web pages get replaced, so you get fresh data. And we didn't bother with anything deeper than 1 day's worth of history. We didn't have any requests to do so. It was understood that customers would have to deal with that themselves and make a copy of the web page if they needed to remember what it used to look like, and so on and so forth. So this is what the web page kind of looks like. In this case, what we're looking at is the main web page on our FRGP web server for the unicast reverse path forwarding checks. And the intent here is that a customer look at this web page, and here are something like 10 customers. And for each customer, we say what router we're talking about. The FRGP has 3 routers. In this case, all of these reports come from the same one. The interface on the router, and it tells the customer how many packets were dropped and how many packets were forwarded. Now, since we're through this process already, we have turned off forwarding, and so all the counts for forwarding are 0. But during the process, and the process lasted several months, those forwarding columns had values in them for packets that we were forwarding, and the dropped column had zeros in it. And then as we turned on some customers and started blocking, the numbers flip-flopped. But this gives the customer an idea how bad the problem is, and also gives them a way to look deeper into it to get details about what the problem is in terms of their leaked packets. So in this case, if I were to click on this 1 million, 5, whatever it is, I would get this web page for a customer named CCCS. And so the way these web pages are organized, the Perl program rolls them up and says, I'm going to put a line on the table for every packet signature that is unique, and I'm only going to do it for the 200 most seen packet signatures on the interface. So the way to read this is to say that for this customer, 66,719 packets were received within the time window, which is shown up there at the top, and those packets, the source address was 10.119.132.233, and the destination was 57.78.226. The source port, the destination port, and the protocol were all the same. And in the last column is a little time window from when the first of those packets were seen to when the last of those packets were seen within the 24-hour time window. Up at the top of the page, it shows the 24-hour time window, and in this case, it pretty much matches. So those packets were sprinkled about and throughout the entire 24 hours. And as you read down the table, you see fewer and fewer packets because we sorted it to the most common packet first. So in this case, the CCCS network administrator would take a look at this and say, oh, I emitted 66,000 of these kind of packets to the FRGP. And it turns out a lot of them are from the same machines. And why is that happening? And one common thing you might think is that, oh, okay, maybe there's a network connected to that customer's edge router, and the edge router has a default route that points at the FRGP, and there's no filters. So if a bad packet like this arrives, that packet couldn't be responded to, of course, because the source address is in RFC 1918 space. It's a private address. So it's stupid to admit that to the FRGP. Nothing's going to happen, but nevertheless, that's what's going on. And the destination port and source port might be a clue to some people as to where that's coming from, but at the least, this customer might consider either just installing filters or on his edge router taking a look at where those packets are coming from in his network and asking why that's happening. So here's another page for another customer. I put this on here to throw out the idea that you see the packet counts there. For this customer, the total was much smaller than it was for the other customer that we just looked at. And you can see that their worst problem is that first top line, and then they have a couple of other hosts that are doing things, but the numbers are going down. So the table is sorted kind of worst first. In other words, look at this first and go see what's going on. So
Pete, I'm going to jump in really quick because there was a question. I think it's relevant. Does uRPF break traceroute? And that's from Jim.
No. Nope.
Okay, easy answer.
The answer is pretty easy because we have this working. In other words, this is all installed and running, and we haven't had problems yet. Let's see. It certainly doesn't break our outbound trace routes, and inbound, I don't think it has a bad effect on inbound trace routes either. So I'll think about that a little harder. I shouldn't say no right off the bat without. Let's put it this way, we haven't had any complaints from any of our customers about it. And please let me know, because the screen I'm looking at only shows the whole thing. So if there are other questions, Jason, please interrupt me.
Okay, will do. We're good for now.
Okay, so the scheme here, of course, is to let the customers, is to gather the statistics, write the web pages, and let that run for several months and tell the customers that you're going to do that. So you started this process, and you say, all we're going to do is log packets. You guys don't need to change anything. And at your leisure, go and take a look and see if you want to do something about this. And some customers did that, and they chose to fix the problem themselves, and then they just disappeared from the web pages, and then they didn't care whether we implemented uRPF or not, because they knew they weren't emitting any bad packets. Turning on the blocking is, we emphasize being flexible and working with our customers. We had customers that, we told them that we were going to start blocking on a certain date, and they said, oh please, can you give us another 2 weeks to go and fix our problems? And we said, okay, fine. And we also said, we're going to tell you the exact day that we turn on blocking on your interface, and we'll back out the instant you tell us something broke, something stopped working on your net. So we're working with them to make this happen. And of course, you can do this one interface at a time. So you can choose, in our case at the FRGP, we chose to do these changes in sort of blocks. We chose about 5 customers at a time, and we had a schedule and a table on the web. And then we mentioned that schedule in our meetings. So there was plenty of warning of various kinds to let customers know what their day was going to be. And then we did 5 customers at once, and that we did that to just sort of keep the confusion to a minimum so that we understood the breadth of what we were doing. And that is another nice feature of the way this is implemented in the Junipers. So you may run into some issues with multiply connected customers, and that's what we talked about earlier with the feasibility kind of thing. You still may end up with some funniness. The biggest funniness that we came up with was some of our customers reported that packets were being dropped by the RPF check. For example, if you were to emit a ping packet to a router, sometimes the return packet, some routers choose to use a source address that isn't the IP address that's on the interface that the ICMP echo came in on. So in other words, the router is emitting a ping response, but it's using a source address that isn't the expected one, and that will screw you up. And so it only ends up hitting ping packets instead of other packets, but packets that go right to the router can get screwed up with this. And to fix that, we use the feature that you saw earlier in the filter this definition of a whitelist. So, I mean, a good example, we have a connection to NOAA. We implemented this, and a few days later learned that our pings were failing, and so we looked into it and discovered that the packets we were getting back that were failing the RPF checks were coming from the correct router, but were coming from another interface on the router than the one that our request had been sent to it. And so we simply added the other interfaces on that router, the other IP addresses, to the whitelist, and it fixed the problem. It does mean we have these whitelists now to maintain, but the truth is, in our case, I don't think we have very many. I think it ends up being something like 8 or 10 IP addresses in those whitelists. And so it's a little irritating, but it's a solution that works for our case. And with that, I have made the Perl program that we wrote available. If you're interested and want to take a look at that, it does contain quite a few lines and sections that are specific to us, but the general gist of the program, it should be pretty easy to take it and modify it to work at another ISP with different customers. And with that, I will open the floor up for questions.
All right, well, thank you, Pete. And while we wait for a couple questions to come in, any way you can just show us a live demo of what it looks like right now? Is there private information that you'd be revealing?
Well, I already was revealing some private information on those 2 other slides. So here's a case of a customer. I mean, I could go to the websites and show you what that looks like if you like. I don't think there's a problem doing that. Let's see. So if I go to our FRGP website and go to the statistics page, that's where we vary this unicast reverse path forwarding checks page. And not surprisingly, there's the page we were just looking at. And if I click on a customer here like this one, that's the full table that's all the packets. It comes down to very few at the end. But for the larger customers here, that one, CCCS had 1,500,000 packets in a 24-hour period. This customer had 7. And so, you could look at that and say, well, 3 of those packets were sourced from that, which is probably like a real source maybe inside somehow it's inside their net somehow. And they were pinging that. And it happened during this time window, which is not quite as large and so that sometimes this can help if we did have customers that went down to the level of trying to emit some bad packets during a little window, waiting 24 hours, and then looking at a table like this and going and using the date time field to zero in on what time of day exactly the packets were emitted. And then they were able to kind of laboriously walk through and tune things and fix things up.
Okay. So we have 2 questions that came in. The first is from Jim again. A cost of uRPF is that every packet needs 2 dips into the forwarding database. This is not a free operation. Turning on uRPF can cut the packet rate of your router in half. If your router is way overpowered, this is okay, but this is not always true. Question, does feasible paths make this worse?
I don't know. That's a very good question. We started out this process and early on decided that if feasible paths didn't work, we wouldn't implement it. So we only ever looked at doing it with feasible paths. And since then we have done it, and we haven't noticed a performance hit. We do have fairly strong routers. These are Juniper MX480s, and I would say I don't think we've noticed any hit on our performance. I understand what Jim's saying. It makes sense that has to happen. The router's obviously doing more work. But I think they've got the logic buried down in the ASICs or something to make it fast enough so that it doesn't cause a performance hit.
Okay. And Greg has more of a comment. Colorado State University is happy with this process and how it is implemented. They thought that they were blocking everything with their own internal RFP checks, but they were missing things. And I guess that goes to my question here. Once you do turn this on for a customer, is there sort of a period of time where there's a whole oodle of them to chase down and then it sort of evens out after that?
Well, what happens is, that's a good point that Greg mentions. We found with our customers that some of them were like convinced going in that they're not leaking any packets. And then they would say, oh, hey, we are. And then they go look and it would end up being some, reasonable misconfiguration or something like that. We didn't really see a lot of events or hits with this system that looked like real DDoS attacks. Where an institution said, whoa, we've got some bad machines or PCs, or we've got real infection problems. What happened more often was it was simply misconfiguration, or it was that pretty common case that I think is the case with CCCS, where they have a default in their edge router and no filters, and so anything that hits the edge router that whether it has bad packets or not, it gets shoved out the interface to the FRGP. And we also had a little bit of what I would call philosophical differences. It was across the spectrum. There were people that thought, oh, we don't want to do this. We don't really want you to do this. We're kind of iffy about it. We lean towards you not doing this just because we don't want you touching our packets, because it might cause some problem that we might run into that we don't like. And there were others that said, oh, this is great. And they did the process that we had kind of hoped they'd do, where they looked at the bad packets statistics and then they implemented their own solutions to it. So by the time we turned on blocking, they had no more packets to block. And there were other customers that just said, we don't have enough time to deal with this. Go ahead and do what you need to do. And you're exactly right that we shouldn't be emitting bad packets, so we doubt that it's going to hurt us once you start blocking them. And we and some of those customers we sort of didn't hear from during the whole process, and so we implemented it and assumed they knew about it and heard about the warnings, and now we're blocking, and we're now feel better about ourselves and our citizenship on the internet.
Okay, great points. So no more questions right now, but we'll ask again. If anybody else has any additional questions, please type them in. So you said that you're running this on your three devices right now.
Yep.
And have you had any other peers of yours in the R&E space start to do the same thing, or no?
Not that we connect to directly that we've heard from. This is one of those areas where I think a lot of regionals are kind of in a place where they have to decide if they've got the horsepower to throw at this problem, or whether they have bigger fish to fry. It's a good thing to do, but when you're done, you haven't solved any performance problems necessarily. I will say that you do have to be a little careful when you turn this on. You might notice that your syslogs fill up like crazy, with millions of packets being logged all of a sudden that weren't before. So it would pay to kind of start off slow and consider your links, consider your customers, how much traffic they're emitting, and start with a small customer, a well understood customer, and see what kind of statistics you get, how many syslogs you get, how long it takes the script to process the file. If the files are starting to be unwieldy, then you could do other solutions to the problem. Of course, you can increase your log rotate times so that you're rotating logs more frequently, but you can often, with a little bit of working with your customers, you can identify a customer that's got a problem and then actually sit down with them and say, well, you got this going on. Can you take a look at this over here? And like I said, some of our customers found things that they didn't expect that their network was doing, and we're happy to go and take care of them themselves.
Okay. Well, I know that there's several regionals that are on this call right now, so maybe you'll get a call from CanRen or WVNet or Three Rocks pretty soon. So
I should have thrown my email address in the slides. I forgot to do that. So my email address, for anyone who cares, is my last name, SIEMSEN, @ucar.edu, and I'll be happy to talk to you about specifics.
Okay. Two more questions came in. June wants to know, for campus network, does turning on uRPF against the internet effective, or is it more useful for turning UPF against the internal network?
Well, so it depends how large a campus you have. I mean, many campuses, a university-sized campus, a large university, might have trouble tracking down things themselves in their own campus network. And for that, you could do, you have to keep in mind that the uRPF is also comparing traffic against routes in the routing table. And so the documentation, the way it talks about it, is it just says examines routes, and I don't know if there's a difference between BGP routes and OSPF routes and ISIS routes or whatever that you use inside your campus. So I'm not sure. I think you would have to experiment to find out. But for a lot of cases, once you've got a signature of the packets that says what the funny packets look like, that would probably help you tracking it down just on a case-by-case basis. And there are things you can do about this problem where a simple fix will take care of millions of packets that are dribbling around. So I don't know that I would implement uRPF inside a campus unless it was a really big campus.
Okay. And Grace wants to know, are you able to export your syslog to network attached storage or anything like that, or do you just have to keep it all on device?
In our case, we have the Front Range GigaPoP has a workstation that's a part of the Front Range GigaPoP deployment, and that workstation is where we house our web server. So that was the natural place to put the syslog files from the routers and the program that parses and deals with those syslog servers, and then it just writes pages out to the files that the web server looks at. And so it was all self-contained into one box. As I said, I think that with a little bit of care about how you deploy this, you don't have to worry too much about exploding syslog files. Usually, if you start to have the problem, you can pretty quickly do something about it. Again, you can turn this stuff on and off, the logging part at least, without really affecting things too much. So I don't think you have to worry too much about the size of the files getting out. You have to think about it. You have to be sensible about it, but you were not going to get gigabytes and gigabytes and gigabytes of log files to where things explode. So I'm not sure if there's another reason maybe to move it off to network storage or something off the server. In our case, it was convenient to keep it all together on one box. And we're small enough, the FRGP is at least, that we're able to work within the confines of that structure.
Okay. Well, I think that's probably it for questions, unless somebody beats me to it before I say goodbye. But thanks again, Pete, for doing this today. I'll post your slides and the recording into the Google Doc, and I'll share that with everybody.
Okay.
And for those that are still listening, next week, Andy Lake from Perf Sonar is going to be doing a talk on the new PS config changes that are out in PS 4.1, I think. So for those that can make that, we'll see you next week. And thanks again, and have a good weekend.
Okay. Bye.